Namaste, everyone. I'm Mehul Girnari, sir, from the IC department right here at AVPTI Rajkot. Welcome to this explainer. Today, we're diving straight into Unit 5 of your FICE syllabus. But listen, this isn't just about scoring those 14 marks on your exam. We're talking about industrial safety. This is the real deal. Out there in the field, a tiny mistake doesn't just mean a failed grade. It can trigger an absolute disaster. So let's get serious and jump right in. To all my Semester 1 students tuning in, I want you to burn this golden rule into your memory right now. DCS runs production, but SIS saves lives. They are absolutely not the same thing. Look, your basic process control system, the DCS, that's your moneymaker. It keeps normal operations running smoothly and generates profit. But when things go entirely wrong, the DCS isn't going to save you. That's exactly where the Safety Instrumented System, or SIS, steps in. And today, we're going to see exactly how it does that. Let's put this into perspective with a real-world scenario. Imagine you're standing at a massive gas terminal. You're looking at a colossal LNG storage tank, and suddenly the level hits 95%. It's literally on the verge of overflowing. At this critical, terrifying moment, an independent safety system kicks in. And you know how much time it has? 2 seconds. Just 2 seconds to trigger the emergency shutdown valve and stop the whole process. If it misses that window, the results would be catastrophic. That right there is the immense gravity of industrial safety. All right, so here's our roadmap for the day. We'll be walking through the safety chain, hazardous zones, gas and temperature classifications, and how we actually protect our equipment. Then we'll wrap up with SIS voting logic and emergency shutdowns. We've got a lot of ground to cover, so let's get right to it. Section 1. The safety chain. In any industrial plant, you never, ever rely on just a single layer of protection. It's all about building a layered defense, kind of like a fortress. So how does a safety event actually play out? Well, first, a risk emerges. Instantly, our sensors handle the detection. If things start getting sketchy, an alarm goes off in the control room. Now, if the operator doesn't catch it or can't fix it, an automatic interlock steps in. And if the situation completely spirals out of control, that's when the SIS takes over, triggering an emergency shutdown to force the entire plant into a completely safe state. It's a precise, step-by-step chain reaction designed to save the day. Moving on to Section 2, hazardous area zones. Look, before you can engineer any safety system, you have to understand the environment you're dealing with. To do that, we rely heavily on the IEC 60079 international standards. This is where it gets really interesting, comparing gas hazards to dust hazards. Take Zone 0, for instance. That's a place where flammable gas is continuously present, like the inside of a massive storage tank. The exact equivalent for combustible dust is Zone 20. Picture the inside of a huge grain silo. Then you have Zones 1 and 21, where hazards are probable during normal operations. Finally, Zones 2 and 22 are places where hazards aren't likely, unless something completely abnormal happens. Where you install your equipment entirely depends on these specific zones. And just like zones, gases themselves are classified into groups. Group 2A contains gases like propane. They're risky, but manageable. But then you drop down to Group IC. This is the highly dangerous stuff, like hydrogen and acetylene. Why? Because their ignition energy is insanely low. Literally, the tiniest invisible spark could trigger a massive explosion. That is exactly why any equipment placed in a Group IC environment has to be the strongest, most stringently tested gear available. Beyond sparks, we also have to worry about pure heat. That's where T classifications come in. The rule here is simple but absolute. The maximum surface temperature of your equipment must stay below the auto-ignition temperature of the surrounding gas. No exceptions. So if you're working with something highly volatile like diethyl ether, you absolutely must use T6 rated equipment, because a T6 rating guarantees the equipment surface temperature will never ever exceed 85 degrees Celsius. All right, Section 3, equipment protection. We know the hazards, we know the zones. Now, how do we actually build the armor? How do we keep our sensitive electrical instruments from causing a disaster inside these dangerous areas? Let's break it down. We basically have 4 main protection methods. XI uses Zener barriers to restrict electrical energy. XD is your flame-proof method. It uses a heavy, robust enclosure that literally contains any internal explosion, so it can't escape into the plant. XP is pressurization. We keep clean air pumped into the panel at a slightly higher pressure, so dangerous gases can't sneak in. And finally, XE stands for increased safety, which just means adding extra mechanical protection to prevent arcs or sparks from happening in the first place. But out of all of these, the absolute gold standard is intrinsic safety, or XI. Here, we restrict the electrical energy flowing through the circuit so drastically that even if there's a short circuit, a spark literally cannot form. It just doesn't have the juice. It's the only method that is 100% safe to use in the absolute most dangerous environment, Zone 0. You can even do live maintenance on it with the power still on. It's practically foolproof. Section 4, the brains of safety. We're moving from the physical armor to the system's logic. This is the brain that reads the data, thinks on its feet, and acts at lightning speed to prevent a disaster. I'm talking about the Safety Instrumented System, or SIS. And the absolute most crucial word to remember here is independent. It operates entirely separately from your basic process control system. Think of it as a vigilant, untouched watchdog. Even if your main plant controller completely crashes, this independent system will automatically step in and force the process into a safe state. The architecture of an SIS is actually incredibly simple, which is exactly what makes it so reliable. It only has 3 main components. First, dedicated sensors that are purely there to detect hazards. Second, the logic solver, which is usually a safety PLC that decides what action to take. And third, the final elements, like those massive shutoff valves, which physically stop the process in its tracks. Now, how do we know we can actually trust this system with our lives? We measure its reliability using SIL, the safety integrity level. It's a scale from 1 to 4. The higher the SIL number, the greater the risk reduction. And yeah, the much higher the cost. Remember that LNG terminal we talked about earlier? An environment like that demands a SIL 3 rating, which means the system has to provide a massive risk reduction factor of up to 10,000 times. To achieve that extreme level of reliability, we use a brilliant concept called 2 out of 3 voting logic, or 2003. Imagine you have 3 sensors monitoring a tank. The safety alarm will only trigger if at least 2 of those 3 sensors detect a problem. Why do we do this? Well, if one single sensor just glitches, we don't want to accidentally shut down a multi-million-dollar plant. But at the same time, we still have incredibly high confidence that if a real danger is present, we're going to catch it. It's the perfect balance. Which brings us to Section 5, the ultimate failsafe. This is for when the logic system decides that things have gone too far and normal operations must cease immediately. A lot of people get confused between a normal process trip and an emergency shutdown, or ESD. Let's clear that up right now. If a pump gets a little too hot and trips offline, that's just a normal trip. Its only job is to protect that specific piece of machinery. An ESD is totally different. An ESD shuts down the entire plant. It's not trying to save a machine. It's trying to save human lives, prevent a toxic release into the environment, and stop a catastrophic explosion. In a way, it's the ultimate act of industrial sustainability. Now, if the absolute worst-case scenario happens and a fire breaks out, you need to know exactly which suppression agent to use. You can't just spray water on everything. Water sprinklers are fine for general cooling, but for a highly flammable hydrocarbon fire, you need foam. For those expensive, sensitive electronics in the control room, you use CO2 or a clean agent gas. And for smaller, localized fires, dry chemical powder does the trick. As a competent engineer, matching the exact right tool to the hazard is your job. All right, as we wrap up this explainer, I want to leave you with one final thought. When you graduate and step out into the industry, your job isn't just about wiring up panels or calibrating sensors. Never forget this. A truly great instrument engineer keeps the people, the machinery, and the planet completely safe. That's your true responsibility. Keep that in mind as you study. Thanks for tuning in, and best of luck on your exams.